Okay, good morning everyone. Thank you again for coming immediately after the conference dinner. Head has very conveniently gave me an introduction to the Ediacaran acanthomorphic acritarchs and pointed out as well some of the reasons why they're particularly important. At the beginning of the Ediacaran, we find a sudden diversification of large acanthomorphic acritarchs, so similar to the things that Head has been showing, but unlike throughout most of the Proterozoic, they rapidly diversify through the first half of the Ediacaran. And this makes them important not only because the Ediacaran is a transitional period for biogeochemical systems from the Proterozoic to the Phanerozoic, but also because they represent the first possible organisms that can be used for biostratigraphy essentially in Earth history on a finer scale. They have the potential to be biostratigraphic tools. It's not that they have yet been conclusively shown to do that yet. So we need to know something about the acanthomorphic acritarchs if we're actually going to use them in any way, in any real way for biostratigraphy. We need to know what their distribution is like. And so far, all the acanthomorphs in the Ediacaran are restricted to low-energy, shallow marine conditions. This diagram here shows the Dushanta Formation, this rimmed carbonate platform, and all of the sections that go through the Dushanta Formation they vary throughout and occur also on the slope and in the basin, but the only ones that find acanthomorphs are on the shelf itself. And this occurs in every single section and every part of the Ediacaran world that people have gone to. And in all of these localities, the acanthomorphs only occur in 3 different lithologies: chert, phosphorite, and shale. These are the standard 3. So the headmark group is one of these localities in which acanthomorphs have been found, and this is the material that I've been working on. It is Ediacaran age. It's bounded at the base by detrital zircon age of 620 million years and by a gas gears equivalent tillite about 580 million years halfway up. And the carbonate platform in which these acanthomorphs, the original acanthomorphs came from, is found at the top of the Brotum Formation up into the Biri Formation. It's a mixed slistoclastic carbonate platform. And the actual original phosphorites that these acanthomorphs came from has now been lost. The phosphorites have been entrained into this viscopast conglomerate, which is a submarine fan that prograded into and incised the carbonate platform. So the material we have was all detrital. The conglomerate itself is undoubtedly formed by a series of debris flows. It's laterally extensive submarine fans occurring all the way around the edge of the basin, with really large coarse conglomerates up to 1 meter diameter clasts, mostly of quartz and gneiss. And at the very base, in this lowermost 15-20 meters, we find phosphorite, carbonate, and shale clasts, telling us that these have been entrained from the underlying carbonate platform. And it's within these phosphorites that you find these acanthomorphic acritarchs. Previously, 2 acanthomorphic taxa have been found from the viscopast formation, and in fact the first was found in 1963, which makes it historically the first large acanthomorph we found in the Ediacaran. And from our reinvestigation of these, we've found an additional 17 acanthomorphic taxa, so there's now 19 acanthomorphic taxa, along with several filamentous and spheromorphic forms. And this is far more in keeping with what we'd expect for the Ediacaran diversity of acanthomorphs, and just emphasizes again the potential that these things have for biostratigraphically constraining, correlating sections within the first half of the Ediacaran. All of these microfossils occur in phosphorites that are filled with microbial mats. There's no misconceptions about this. There's clear evidence that these are microbial mats. And what you can see is a sequence of muddy carbonate mud that's been phosphatized, alternating with microbial mats, rich organic material. And acanthomorphic, spheromorphic, and filamentous microfossils are bound within here, within these mats. And you can see in a fair bit of detail, there's a range of morphologies. Some are collapsed, some are well preserved, but they're all undoubtedly bound within the mats. Now, in amongst these, this in itself is fairly consistent with what we expect. But in amongst these, we've found a handful of unusually preserved acritarchs. These are preserved by encrustation of apatites around the inner and outer wall of the acritarch, and with botryoidal apatite filling the inside. And this is consistent when we look if we look in detail at a section. You can see acanthomorphic processes going around the rim of these fossils. So these are acanthomorphic acritarchs preserved in what is essentially the classic Dushanta type preservation. This is the taphonomic window that preserved the Dushanto animal embryo-like fossils. So it's a very significant taphonomic window for Ediacaran paleobiology, it's told us a huge amount from the Deschamps Formation. And this is the second time it's been found, so the first time outside the Deschamps Formation this has been found. But what's interesting about these fossils isn't actually their preservation, it's where they were found. They are again bound within microbial mats, but when we looked at those microbial mats, they were not detrital phosphorite pebbles containing microbial mats. These microbial mats are encrusting the paleosurface of the conglomerate itself. So the mats encrusted the paleosurface, a temporarily abandoned debris flow surface, and then were phosphatized in situ. And so if you look up close at a section there, we can see this sequence here, and there are several erosion surfaces running through this section. And the most important layer is this one in the middle here, and you can see these elongate structures here. These are fenestrae, these are void filling, and these are interpreted as gas bubbles that have been phosphatized, have been trapped in the microbial mats. And this is the layer in particular which we find acanthomorphic and stereomorphic acatarchs. So this is just a basic model. You see we have microbial mats encrusting the conglomerate, encrusting clasts. This is phosphatized and eroded, and then again we have a new layer of microbial mats, which in this case has the acanthomorphs, followed by a continuous sequence of phosphatization, erosion, more microbial mats, and so on and so forth. And you can see that there is still active sedimentation going on. There are still a lot of grains being deposited, being bound within these mats. So it's not an entirely abandoned sedimentary system. There is still detrital material being deposited, just not on quite the same order as meter-sized conglomerate clasts. So what we see, what this means, is that the acanthomorphic acatarchs are bound within living microbial mats that were growing on the conglomerate paleosurface, which means they were active, they were alive during the time of the submarine fan deposition. This is the first time acanthomorphic acatarchs in the Ediacaran have been found living in the environment of a submarine fan in a high energy depositional environment. Previously, they're always found on these muddy substrates, low energy environments. This is as far from a low energy environment as you can possibly get. Meter-sized clasts are not transported easily. And so this is essentially expanding the ecological range of the acanthomorphic acatarchs. Everyone previously assumed that they were restricted to these environments, this carbonate platforms where we have low energy conditions, but this is demonstrably not the case. So having found acanthomorphs within the conglomerate itself, we thought we'd have a further look at what else is here. And the majority of the conglomerate itself, if you're around the outside of this, this view here, this is the interstices of the conglomerate, the carbonate cement that holds it together, and the overall framework of the conglomerate is kind of around this. This is focusing on the interstices itself. And all of these clasts here, they have a circumgranular cement which binds all of the clasts together, which occurred before anything else after the conglomerate was deposited, and then is filled in with pseudosparite. And this is the standard sequence we see throughout. But this darker patch running through here, this is actually not void filling, this is a carbonate sediment which has been recrystallized. And this was deposited on top of those circumgranular cements, which means it came in after the conglomerate was deposited. So in the same way the microbial mats shows that it was at the same time. And what we found that was really surprising is that within here, we find a bunch of acanthomorphic acatarchs in a new taphonomic window for the Ediacaran. So instead of having these three taphonomic windows of phosphorite, chert, and shale, we have carbonate-hosted acatarchs representing a fourth taphonomic window into the Ediacaran. And you can see these are really large, these are really well preserved, very, very detailed preservation. And when you put up, you see several of these clumped together. They are not low diversity, it's not just one form. There are 6 different species of a variety of different process morphologies. And when you look up close at these, you can find some phenomenal process details. You can see this is of 5 micron sized processes marked in the arrows here. And you can see the crystals around them are much, much larger. They are on the order of 30 to 40 microns. And what we would expect from carbonates like this is that these the crystals would just destroy the organics. They would puncture the organic walls, destroy them, degrade them, and we would lose all the material. And this is patently not the case. They are preserved, although they don't look like much from a distance. When you zoom in right up close, you'd be hard pushed to find better preservation than this in a lot of chert and phosphorite material as well. The preservation it's not a step down from the classic chert and phosphorite, it's almost as good. And I wouldn't forgive you for saying, are you sure there's not just a little hint of phosphate or silica or something like that in there? Because that's the first thing you think of. Carbonate isn't meant to preserve acatarchs like this. It shouldn't preserve the organics like this. So, of course, the first thing you do is stick the analyzer in, looking at cross polars, and you can't immediately see anything like that appearing. So when we look in the SEM and look in a bit more detail, you can see in this backscatter image here, this is the fossil itself picked out high density. This is because it's actually void filled. So this is filled in with dolomite and anchorite, which grew in from the acanthomorph wall inside. But surrounding it, you can see these dolomite rhombs picked out here, which are of the carbonate sediment that was recrystallized. So this was recrystallized into dolomite rhombs, and then subsequently recrystallized again to give it the appearance that you see in transmitted light. And we look at the elemental maps. The calcium, magnesium, you can see just showing that there is a lot of calcium, there's a lot of magnesium. This is all dolomite. And if you look at this, the one down here of phosphorus, you can see there are little bits of phosphorus. These two grains here, they're picking out minute amounts of phosphorus. These are not phosphorite grains. These are siliciclastic grains that have a tiny trace amount of phosphorus. So this is obviously a relative abundance elemental map. So the amount of phosphorus that's being picked out in these little patches around here is extremely low. And you can see it actually correlates with these little dark blobs here. It doesn't relate in any way to the preservation of the acanthomorphs. In fact, this is the only specimen that contains any phosphorus at all. The rest of them, there is no indication of anything at all, other than calcium, magnesium, and a bit of iron and manganese. And you can see again from the silica that the fossil itself is completely absent and devoid of silica. It's undoubtedly preserved in carbonate entirely. And as I said before, this is the first time that acanthomorphs have been found preserved in carbonate. So what does this mean in terms of the importance of acanthomorphs? What it tells us is that from two separate lines of evidence, from this second occurrence of Dachanda type preservation in the Ediacaran, where we have microbial mats encrusting the paleosurfaces with acanthomorphs bound within, and within carbonates that must have, carbonate sediment which must have came from the water column above the conglomerate, with acanthomorphs bound within them, that acanthomorphs can and do live and survive in high energy depositional environments. So this is an entirely new discovery. This is something unique both in terms of taphonomy and in terms of ecology. The acanthomorphs are not meant to survive in high energy environments. Generally speaking, we would expect them to be distributed, to be dispersed, or be destroyed. And we also would not expect them to be preserved in carbonate, yet we're finding them combined in both, in really coarse clastic material. And this is a simple comparison. When you look at, this is an example of Dachanda carbonates with some chert nodules. The nodules obviously really nicely preserved, capture the acanthomorphs and keep them safe from any subsequent reworking. Whereas this conglomerate here, I don't imagine anyone here would expect to find sub-millimeter sized organic walled microfossils, single-celled organisms being preserved in this kind of material. It's extremely unlikely, and yet here we have evidence for it. And so this makes the Biscapas a huge outlier in terms of what the kind of features we find of the environment and taphonomy of the Ediacaran acanthomorphs. And so just to reiterate that point, this is the second ever occurrence of Dachanda type preservation. It is the first occurrence of carbonate preservation of acanthomorphic acanthomorphs in the Ediacaran, and potentially opens up a whole new window of exploration. On top of that, from these two independent lines of evidence, we have proof, demonstrable proof, that acanthomorphic acanthomorphs can and do survive in high energy depositional environments, again opening up a new avenue of research to explore conglomerates as a potential taphonomic trap in the Ediacaran for further exploration of acanthomorphs in the Ediacaran, and that this expands their ecological range. And overall, this changes how we must view the acanthomorphic acanthomorphs in terms of where they are restricted geographically and stratigraphically. Thank you.